Hello there, students and friends. This is the fourth sequel of my lecture series on AC circuits. It focuses on the concept of resonance in an RLC series circuit connected to an AC source. So just stick around, watch and learn. One practical importance of RLC series circuit is the way it responds to sources of different angular frequency omega. For example, one type of tuning circuit used in radio receivers, like the one shown in the figure, is simply an RLC series circuit. A radio signal of any given frequency produces a current of the same frequency in the receiver circuit, but the amplitude of the current is greatest if the signal frequency equals the particular frequency to which the receiver circuit is tuned. This effect is called resonance. The circuit is designed so that signals at other than the tuned frequency produce currents that are too small to make an audible sound come out of the radio's speakers. To see how an RLC series circuit can be used in this way, we connect an AC source with constant voltage amplitude capital V, but adjustable angular frequency omega across an RLC series circuit. The current that appears in the circuit has the same angular frequency as the source and the current amplitude capital I equals capital B over capital Z, where capital Z is the impedance of the RLC series circuit. This impedance depends on the frequency. The figure shows graphs of the resistance big R, the reactances capital X of L and X of Z, and the impedance Z as functions of omega. Right? So, uh, the angular frequency along the x-axis is in terms of the logarithmic value. This is to enable us to have a bigger range for the omega. And as you can see, the resistance capital R as a function of omega is constant. This is the straight horizontal graph line for the resistance. And for the inductive reactance X sub L, you will see here that as the angular frequency increases, the inductive reactance also increases, while the capacitive inductance decreases. Okay? And you will notice that the impedance has the least value, all right, at a certain angular frequency where the two reactances, X of C and X of L, are numerically equal. And we take note that as the frequency increases, the inductive reactance XL increases while the positive inductance decreases. So there is only one frequency at which XL and XC are equal. And this frequency is known as the resonance angular frequency omega naught, where this omega naught or angular resonance angular frequency is just equal to the reciprocal of the square root of the product of inductance and capacitance. Now, at resonance, the voltage and the current are said to be in phase. In other words, the angle between them is equal to 0, and that the impedance is at its lowest value equal to the resistance, capital Z is equal to capital R. So that means the impedance can also be expressed as the voltage amplitude, capital B, divided by the current amplitude, capital I. Question number 1. In an RLC series circuit, like the one shown in the diagram, the source is operated at its resonance angular frequency. At this frequency, the reactance, capital X sub C, of the capacitor is 200 ohms, and the voltage amplitude across the capacitor is 600 volts. The circuit has resistance, capital R, equal to 300 ohms. Question is, what is the voltage amplitude of this AC source? Okay, so for our solution, we say that the source is at resonance frequency omega naught, right? So we first calculate the current amplitude, which is capital I equals the voltage across the capacitor, capital V sub C, divided by the capacitive reactance, capital X sub C. Substituting, we have 600 volts. This is the voltage across the capacitor. It's given in the question. And then divided by the capacitive reactance of 200 ohms. So the current amplitude, capital I, is equal to 3 amperes. Alright? So at resonance frequency omega naught, we say that the impedance, capital Z, is just equal to the resistance, capital R, which is 300 ohms. Okay? And also, we can say that the capacitive reactance, capital X sub C, is equal to the inductive reactance, capital X sub L, which is 200 ohms. So we can now determine, okay, the target variable, which is the voltage amplitude of the source. We simply multiply the impedance, capital C, and the current amplitude, capital I. That is, the value of the impedance is 300 ohms multiplied by the current amplitude, which is 3 amperes. So we get the value of the voltage amplitude of the source equal to 900 volts. Moving on to question number 2. You have a 200 ohm resistor, a 0.400 Henry inductor, a 5.00 microfarad capacitor, and a variable frequency AC source with an amplitude of 3.00 volts. You connect all 4 elements together to form a series circuit. Question letter A. At what frequency will the current in the circuit be greatest? What will be the current amplitude at this frequency? Question letter B. What will be the current amplitude at an angular frequency of 400 radians per second? At this frequency, will the source voltage lead or lag the current? So, our solution for question letter A, we have to determine the resonance angular frequency omega naught, which is equal to 1 over the square root of the product of the inductance and the capacitance. And substituting, we have 1 over square root of 0.400 Henry multiplied by the capacitance 5.00 times 10 to the negative 6 farad. Simplifying, we'll get the value of omega naught equal to 707 radians per second. And then we will determine the ordinary frequency, small letter f, which is just equal to the resonance angular frequency omega naught divided by 2 pi, or it is simply 707 radian per second divided by 2 pi, and simplifying, we get the value of the ordinary frequency, small letter f, equal to 113 hertz. And the value of the current amplitude corresponding to this frequency is just dividing the voltage amplitude, capital B, by the resistance, capital R. And so we get 3.00 volts divided by 200 ohms, or current amplitude equal to 15.0 milliamperes. Okay, moving on with our solution. For question letter B, we are required to determine the current amplitude, capital I, at a given angular frequency omega equals 400 radian per second. We first determine the capacitive reactance, denoted by capital X sub C, which is just the reciprocal of the product of this angular frequency multiplied by the capacitance C, or 1 over 400 radian per second, to be multiplied by 5.00 times 10 to the negative 6 farad. Doing our math, we get the value of the capacitive reactance equal to 500 ohms. Next, we also determine the inductive reactance, capital X sub L, which is simply the product of the amplitude or angular frequency omega by the inductance, capital L. And so, substituting, we have 400 radian per second to be multiplied by the inductance 0.400 Henry. Simplifying, we will get the inductive reactance, capital X of L, equal to 160 ohms. So, we determine the impedance, capital Z, whose original formula is equal to square root of R squared plus the square of the difference between the inductive reactance and the capacitive reactance. Right? So if we do that, we have square root of 200 ohms to be squared plus 160 ohms minus 500 ohms, their difference to be squared. Alright? Simplifying, we will get the value for the impedance, capital Z, equal to 394 ohms. And using the relationship between the current amplitude to the impedance, which is simply capital I equals capital V, which is the voltage amplitude, divided by the impedance, capital Z, we have the value for the current amplitude, capital I, equal to 3.00 volts divided by 394 ohms, or equal to 7.61 milliamperes. Right. And the final question, whether the voltage lags or leads the current our answer is the voltage source lags the current because uh, we determined that the angular frequency, which is 400 radians per second, is less than, all right, less than the resonance angular frequency omega naught. And that means the capacitive reactance capital X of C is also greater than the inductive reactance capital X of L. We say that the voltage source indeed lags the current. We're down to our last question, number 3. An RLC series circuit has resistance capital R equal to 400 ohms, inductance capital L of 0.600 Henry, and capacitance capital C equal to 5.00 times 10 to the negative 8 farad. The voltage amplitude of the source is 80.0 volts. When the source operates at the resonance frequency of the circuit, what is the average power delivered by the source? So for our solution, we determine the resonance angular frequency omega naught equal to 1 over square root of LC. Substituting, we have 1 over square root of 0.600 Henry times 5.00 raised to the negative 8 power farad. And we get the value for omega naught equal to 5,774 radians per second. All right. So, conceptually, it's already clear that the phase angle phi between the voltage source and the current is equal to 0. Okay, that is the concept for a situation where the resonance frequency, where the angular frequency is equal to the resonance frequency. All right, but just to make sure that the value of the phase angle P really is equal to 0, let's try using the formula for getting the phase angle phi using the formula arctangent. All right, arctangent of the ratio resonance frequency omega naught times L minus 1 over omega naught capital C divided by the resistance R. Substituting, all right, we get the arctan of the product of the resonance frequency omega naught earlier calculated as 5,774 radians per second, multiply that by the value of the inductance given 0.600 Henry, and then minus the reciprocal of the product of the resonance frequency 5774 radians per second and the capacitance, which is also given 5.00 raised to the negative 8 farad, then all over the resistance R. Simplifying, you will notice that the product of omega naught, all right, and the inductance will result to 3,464. Likewise, the result of getting the reciprocal of the product of omega naught and the capacitance will also result to the same number, 3,464, which when subtracted, of course, we get 0. That means when we get the arctangent of 0, all right, that's automatically equal to 0. In other words, this phase angle P indeed is equal to 0. So we emphasize that at resonance, the voltage and the current are in phase, meaning the phase angle between them, angle P, is really equal to 0. And rounding up our solution, at resonance frequency, we say that the impedance, capital C, is just equal to the resistance, big R, which is given as 400 ohms. So we can determine the current amplitude, capital I, which is just equal to the voltage amplitude, capital B, divided by the impedance, capital C. In substituting, that's 80.0 volts divided by 400 ohms, all right, for a value of 0.200 amperes as our current amplitude. And finally, we can use the formula for determining the average power, okay, equal to 1/2 of the voltage amplitude and the current amplitude multiplied by the cosine of angle phi. All right. Substituting, we have 1/2 of the voltage amplitude, 80.0 volts, times current amplitude, which is 0.200 amperes, and the cosine of 0 is understood to be equal to 1. So the average power is equal to 8.00 watts. So that completes our answers for all the questions in this video tutorial. But before we go, we emphasize the key concept that we applied in this particular question number 3. We say that in an AC circuit, the current amplitude is maximum for a given source voltage amplitude when the source frequency is equal to the circuit's resonance frequency. For a series RLC circuit, the resonance frequency is the same as the circuit's natural oscillation frequency without the resistor or the source. That's it. Thank you very much, as usual, for your indulgence. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.